Next-generation computing provides a high-level overview of emerging next-generation computing models. They identify domains that can be areas of interest for further research and discuss current computing technology. They explore four main categories with various subtopics. Biocomputing section utilized the largest dataset. This subset includes articles regarding DNA, molecular computing, and brain-inspired computing. Biocomputing is a major subset of natural computing and focuses primarily on biological systems. So, biological systems can process information like a computer. We could use algorithms to mimic their behavior and even compute on biological entities directly. However, computing with biological entities comes with problems such as unexpected contamination and a lack of information about the biological entities themselves. Limited knowledge on the differences and similarities of computing machines and biological entities is a core issue. The algorithms mainly used in biocomputing consist of swarm intelligence, membrane computing when using P systems, mimetic computing, cellular automa, and DNA and molecular computing. Over on the right is a simple GIF of the swarm intelligence algorithm being used. There's three entities, a base entity here in the middle. The smaller dots are agents, and then we have value entities, and the agents search randomly for a value, and once they find it, they alert the other entities, and it brings it back to the base efficiently. So you could think of this kind of like an ant colony in like just biology, where the ants are the agents and they search randomly for some food, and once they randomly find it, they'll alert all the other ants and they bring it back to the base. The three major subsets included in this study include membrane computing with P systems, DNA computing, and neuromorphic computing. Membrane computing abstracts from the design of biological membranes, particularly the compartmentalized nature of the internal structure that's affected by membranes. The modeling computational systems based on membranes are referred to as P systems. The P system model was introduced by George Paun of the Romanian Academy in 1998. We use mathematical models such as P systems to mimic the framework of a living cell. Our understanding of cell architecture is always increasing, leading to dynamic evolution rules. Membrane computing has many uses in biology, such as modeling photosynthesis, signaling pathways, cell-mediated immunity, and more. And it involves cell-mediated immunity involves programming cells to produce antibodies for antigen. And membrane computing also provides a wide range of uses in computer science, such as for graphics, cryptography, and solving NP problems. DNA computing is based on the notion that data can be encoded as biomolecules such as DNA and RNA strands. They could be transformed through molecular biology tools to perform arithmetic and logical operations. So you could think of these strands as memories, and they're altered using CPU-like tools that perform operations on them. Neuromorphic computing works similarly to membrane computing, but instead of being modeled on membranes usage in cells, it's modeled on the human brain and uses systems built from devices that are supposed to mimic neurons. The next area of computing this paper focuses on is nanocomputing, which consists of computing at a molecular level. The two main subtopics in this area is quantum dot cellular automa and nanomagnetic logic. Quantum dot cellular automa represents binary information in cells using electromagnetic fields. In the diagram, it shows information being represented using these dots that consist of an electron or no electron, and how they're arranged is how they process information. They have very low power consumption when compared to traditional computing. The next subtopic is nanomagnetic logic, and it's an implementation of QCA, where it uses magnetic fields to represent information, but it has some disadvantages, including it being unreliable, having low processing speed, and higher latency.
Hello, this is Aidan Abelard, and I'll be presenting on the spintronics and photonics section in Scientometric Study on Next-Generation Computing. Spintronics is a branch of electronics that focuses on storing and computing using the spin of electrons instead of the electrons themselves. Spin is a property of electrons that can be measured and manipulated using electromagnetic waves. What is an MTJ? The most important component relating to spintronics is the MTJ, or the magnetic tunnel junction, which is able to encode the logic bits 0 and 1 by storing or setting the spin of electrons. It is made up of 3 layers, 2 ferromagnetic electrode layers, and a thin insulator or barrier layer in between them. One of the electrode layers is used as a reference layer, and the other is a free or storage layer. And you can see illustrations of them over here. In an MTJ, electrons in the reference layer always stay in the same state, while ones in the storage layer can either have parallel or opposite spin to them based on if current is flowing through the barrier layer. Current that flows through the barrier layer is known as tunneling current. Tunneling current is used to change the spin and therefore binary state of the storage layer based on the direction that it flows in from. When tunneling current flows in from the reference layer side of the MTJ and successfully reaches the storage layer side, the storage layer becomes aligned with the reference layer and for the purposes of computing can be treated as a binary 1. When it flows in from the opposite direction, i.e. directly to the storage layer, it becomes anti-parallel to the reference layer, which can be regarded as a binary 0. Over here you can see the tunneling current going in through the MTJ. There's also a control current that goes through the bottom and runs across the free layer. What is spin torque? In the context of an MTJ, when tunneling current passes through the barrier layer, it becomes spin polarized, which means its spin is either completely aligned or oppositely aligned with the spin of the electrons in the reference layer. This polarization generates a torque known as spin torque. Spin torque is what enables the tunneling current to switch the magnetization of the storage layer. Spin transfer torque, STT, is a property of electrons that causes them to align their spins with one another and close to each other, caused by the previously defined spin torque. It is what allows for the creation of technology such as STT-MRAM, which stands for Spin Transfer Torque Magnetic Random Access Memory, and this is proven to be a successful next-generation memory alternative. And over there is a figure of spin transfer torque in action, and the formula behind it. Modern applications, so further going into MRAM and STT-MRAM, magnetic random access memory are becoming more, and STT-MRAM are becoming more and more widely used currently due to their unlimited high-speed reading and writing endurance, low power consumption, and most importantly, their lack of volatility. Lack of volatility in MRAM means that its state can be preserved without the need for an external power source by using the magnetism of MTJs and other spintronic components to its advantage. Moving on to the photonics section, optical computing, also commonly referred to as photonic computing, is the use of photons instead of electrons entirely to perform logical or computational tasks inside of computers. Though photons are uniquely suited to this task due to their unparalleled speed and low heat generation, there are still a number of problems that come with using them to recreate and replace various components that were previously designed with the use of electrons in mind. One of these problems is that light tends to spread out, which is why photonic technology wasn't used until the 90s, when fiber optic cables were first used to achieve ultra-high speed data transfer. Think stuff like internet cables under the ocean and stuff like that. These cables allow for trapping and focusing of light into one channel or circuit, so to speak. So over here is an optical fiber, and it was the first step towards the invention of the aforementioned optical cables. It's a thin slice of material, usually glass or plastic, that is able to channel light along its length, effectively allowing for the safe guidance of light and preventing it from spreading out, so you can focus light and transmit it along the fibers. This channeling of photons is crucial for efficient and reliable data transport. They're also immune to electromagnetic resistance, which is a problem that can be experienced when guiding electromagnetic waves instead of light. So, an application of photonics is wavelength division multiplexing. Traditionally, multiplexers require complex circuits with many paths to allow electrons to perform the necessary calculations. The wavelength division multiplexer, WDM, allows for a vast efficiency improvement in optical multiplexing by refracting multiple colors or wavelengths of light into a single optical fiber, which could then be separated again later. New opportunities for parallel computation also emerge from WDM. So over here you can see it in action, where you have multiple rays of light coming in to the multiplexer, which is basically just a prism that will refract the light and combine it into one beam, and then the information could then be extracted back out using another multiplexer or another component of the multiplexer, which is basically a prism that extracts the light. It comes out separately, as you can see here. Nanophotonics and plasmonics. So, nanophotonics is a field of photonics that incorporates principles of nanocomputing into photonic chip architecture. In general, the smaller you build photonic circuits, the harder it is to keep photons from leaking out. Since their enclosing material, the edges of the optical fibers are thinner. To prevent this, metallic nanophotonics poses a possible solution by entailing the use of metals for built-in optical waveguides instead. Plasmonics is a branch of nanophotonics that focuses on the exploitation of surface plasmon polaritons, SPPs, in nanostructures. SPPs are the parent of electromagnetic waves to the motion of free electrons in between a dielectric and a metallic material. They can overcome the diffraction limits of light by confining and guiding light at previously impossible nanometric scales. You can see an illustration of the SPPs over here and how they work in regards to electromagnetics. Metamaterials. Since nanophotonics has allowed for the guidance of light, therefore photons at sub-wavelength scales Metamaterials were created to assist in limiting the absorption losses caused by light propagation in the third dimension. Metamaterials are synthesized materials that have